thanks everyone for being back after the very, very short break. I'm Sara Benetti. I'm head of School of Geography and NDS. Sorry, I'm the head of school. I'm a marine scientist, and I've actually, funny enough, been working on the Irish glacial landscape for the last 15, 16 years now. So it's a strange combination. There's no geography actually taught at GCSE or A levels in Italy as a standalone subject, and there's no geography degree in Italy. So it was quite a surprise to come over to the UK and find it as such, as a standalone subject. It's embedded in other disciplines. It would be part of geology, part of science, part of other things, but there's no geography curriculum. So for me, it's been a learning curve over the years to learn about what is actually taught in geography here. And I think my research and what I do and what I teach here actually aligns well with the geography curriculum. So I researched the glacial landscape, and I could see that it was one of the topics of the GCSE exam papers. So I'll take you through basically more or less how I teach my students in terms of the glacial landscape of Ireland. But we are not only staying onshore, we're also moving offshore, which is where most of my interest is. So it's a kind of summarized lecture that can apply to your students as well, obviously at different levels, with some resources as well. So I always start by pointing out that Earth history is much longer than just the last 20 or 150,000 years. We are Earth is billions of years old, and actually we have evidence of more extreme climates than we have today or that we've had during the Quaternary throughout the last several millions of years. So we go from very, very extreme cold conditions, what's called the snowball Earth theory, where Earth was mostly covered in ice. And although it's quite controversial still, there's evidence in places like Australia and Africa of glacial sediments that date back from 700 million of years ago. We then go from such really extreme cold conditions, much colder than today, to conditions like the Cretaceous greenhouse, where it's actually much warmer than today. There's hardly any ice. We have ferns and flowers growing at the poles and so on. So we start from that. We know that there's extreme variations over Earth climate over time. So we constantly switch between cold and warm, cold and warm. But then as we come into the Quaternary, so the last 2.6 million of years ago, we see, again, lots of smaller variations in climate between glacial and interglacial conditions. And even the timing of those cycles changes throughout the Quaternary. But really then we focus on what happened during the last glacial period. So from around the last interglacial at 125,000 years ago up to present. And we know that at this time we had the transition from glacial conditions where most of the northern and southern latitudes were covered in ice to modern conditions where we have much more constrained ice caps and ice sheets over Greenland and Antarctica, and glaciers only at high latitudes. So this is how we get to the last 2.6 million years. And really what we want to see is how this last, perhaps, glacial period has impacted on the landscape that we see today. I find it always very interesting, and I always point out how people up to 200 years ago thought that the Earth had always been what they saw at the time. And there's been only an awareness in the last 150, 170 years that maybe what we see in the landscape has been shaped by processes that are very different to what exists today in the same landscape. I remember myself as a secondary school student being told about these erratics that are found in Italy, south of Lake Garda, that were brought there by glaciers. So it's a bit the same. That's the evolution of what we know about the glacial theories. So there's just a summary there of how different people started piecing different pieces of the puzzle together, going from landscape to biological evidence. But really what we have experienced in the last 60 years are really big pushes in methodological techniques that we can use to actually see landscapes at different scales. So before we could only view the landscape by walking around it, then we moved on to area photographs and satellite imagery. So suddenly we went from something that we could just see with our eyes as we walked around to having a really large-scale view of the landscape that we didn't have before. There's also been advances into how we can date the sediments and what we find in the sediments, fossils, or how we can date rocks. We managed in the last 60 to 70 years to acquire samples from the deep sea that are actually revealing a lot about the history of ice sheets in the past. And we started coring through glaciers and ice sheets and so on. And again, we started finding out how things have changed in the past through these proxies. So I thought I'd put a few resources that you might not be aware of that might be relevant. The Irish Quaternary Association has actually created a booklet and a workbook for secondary school pupils about glaciations and how during the Quaternary that has affected the Irish landscape. So you have the link here, and I'm sure Paul will share the presentations and the links anyway. But that's one way to really focus onto the Quaternary and give your students maybe something useful to work on. But as a scientist, my point is always, why are we studying ice sheets? Who cares, basically, what shape the landscape, unless you're really interested in that landscape. And the reason why we're studying past ice sheets is that they provide an excellent analog for what might be happening to the modern ice sheets. So we know from satellite imagery over time that Antarctica has been steadily losing ice over the last even 50 to 60 years. This is just a snapshot of the last 20 years that is showing how the mass of ice in Antarctica is changing, but also mostly where it's changing. Okay, and the area of West Antarctica, it's where most of the ice loss is happening. And one key reason why that ice loss is happening there is that that portion of Antarctic ice sheet is actually based underneath sea level. So the base of the West Antarctic ice sheet might be a few hundred meters below sea level. So that then generates an additional instability. It's something that's referred to in the literature as marine-based ice sheet instability hypothesis, but we know this is what's happening. So if we have ice that's grounded below sea level, which is there, and it starts losing ice for changes in climate, for changes in oceanographic conditions and so on, once it starts losing ice mass there, that profile becomes steeper, and that destabilizes further the ice margin. So once that grounding line starts retreating because of drivers of change that are outside the ice sheet, climate currents and so on, then that ice sheet is destabilized even further and loses more mass than it will lose just based on the climatic conditions. And this is what we're seeing in Antarctica. But what we have, if we think about Antarctica and Greenland, is actually a very, very short kind of time frame. So really, we want to look at the past ice sheet because they provide a long-term baseline to study what's happening to modern ice sheets. We also know that if some of these ice sheets were to melt, sea level would significantly increase. So we're not talking about 10 centimeters, 20 centimeters. We're talking about meters of sea level rise. If we think about the entire Antarctic ice sheets, it's basically packing about 66 meters of sea level globally. And then Greenland is about 7 meters. We also know that there are changes in ocean currents at the moment, for example, weakening of thermoline circulation across the North Atlantic, and that actually can accelerate ice melt as well. And the key thing is that we don't know all of the thresholds, so we don't know exactly at this moment in time how much can the ice sheet itself kind of continue to change without changing dramatically and forever. So really we want to look at the past ice caps and ice sheets to help us forecast what's happening to the modern ice sheets. And really one point that I always like to make is that these things have happened in the past. We talked about snowball Earth and the Cretaceous greenhouse world and so on, but humans were not living in that past. We were not living on coasts. We were not impacted by these changes, and that's why we want to know more about these things. So how can we reconstruct changes in quaternary ice sheets and glacial systems? We look at the landscape. We look at the geomorphological evidence. So the landforms that we see gives us clue about the processes that shape that landscape. And the relic landforms that we see visible today are ones that were created by processes that were happening in the past. However, we can get an idea of the processes by the landforms alone, but we can't date them. So we don't know what their age is just by looking at them. They might provide a large-scale sequence of what was happening, but not a fine scale. They only show environmental change in terms of physical environment and not ecological environment. And not all changes actually leave a geomorphological trace, and also landforms can be eroded away. So normally, when we're doing this kind of reconstructions, we pair up the geomorphological evidence with the sedimentary evidence, because those sediments can include different type of information, from biological to chemical to the fine-grained changes that were happening. And sediments can be examined in the field and can also be taken back to the lab for analysis. So in terms of landforms, there's so many different kinds of landforms, glacial landforms out there. Most of these are actually visible even within the island of Ireland. But interestingly, they can be classified as an erosional landform, so where things are moved away and form certain shapes, striations, whalebacks, cirques, and so on, and the positional landforms that are often divided in glacial or glacial-fluvial, and ice marginals of glacier. So these are landforms that are created by ice sheets pushing sediment around. But the interesting thing about all of these landforms is that they give us information about different characteristics of an ice sheet. And also the things that complicates reconstructions is that although we have distinct landforms, we also have modifications. So really, as ice moves across an area, it might form rip moraines at one stage, and then drumlins further downstream, and then megaflutes further downstream. But we will have bits in between where those landforms will be kind of a mixed shape. So it makes things a little bit more complicated. But really, we have looking at all of these landforms, we can get information, for example, about the lateral extent of the ice sheet. So terminal or end moraines are formed where the ice margin was pushing sediments to, the ice was pushing sediment to its margin. There's a large moraine system going across the south of Ireland called the Southern Ireland End Moraine, which is more or less where we thought the ice sheet was coming to, although there was an ice cap here in Kerry and Cork. We can use streamlines to know how thick the ice sheet was. We have some good examples of streamlines around Ireland. For example, in Connemara, people have looked at ice-covered bedrock and weathered debris, and they have worked out how the ice margin was kind of becoming to lower altitudes, and therefore started thinking that maybe the ice was flowing at one point offshore and not stopping at the coastline. So really we have some good information about the lateral extent, but also the shape and how these landforms are aligned give us an indication about ice flow direction. So we have striation and ice molded bedrock. We have streamlined glacial landforms like drumlins and mega-scale glacial lineations that are aligned in the direction of the ice flow, and things like erratics that will tell us in which direction the ice sheet was going. The interesting thing about landforms like drumlins and megascale glacial lineations is that they also suggest how fast the ice was flowing. So if I see drumlins or megascale glacial lineations, I always think about a fast-flowing area of an ice sheet that then can link back to those fast-flowing parts of West Antarctic ice sheets, for example, that are wasting away at the moment. Once we see how these landforms overlap and are modified by one another, we can also start to reconstruct ice flow dynamics and how the ice flow direction change over time, and how the ice speed has changed over time. So really the glacial landscape of Ireland has been mapped in lots of detail, and we'll see an example in a second. But going from mapping of different glacial landforms, we can actually go to flow sets. And those flow sets represent how the ice was shifting over time. So how basically where it was thicker at one point in time and flowing, and then maybe after it flowed for it wasted away for a while, it changed slightly the area where it was thickest. So we start reconstructing different time slices of ice over time. As I said, really the ice sheets, the Irish landscape is dotted by landforms. This is a map that some of you, or hopefully most of you, have in their pack already. And you can use it, and you can also access it online. I always like to put a picture of myself. My children have been subject to these discussions for years and years. But really, let me show you. So this map has been created as part of a project led by Sheffield University. It's called Brick Ice, and you can access it online here. If you zoom in and out, it will bring up the different features at different resolution, and you'll be able to click on different features as well and get information about them. So you find the different features here, and you'll also be able to zoom in. And as you zoom farther and farther in, you can click on the different features and find information about them, and you can zoom to them too. So it really gives an indication of the different scale at which these features are and where they are in space, and it's a good starting point to know where things are. You can also get an S3 story map about glaciation, which is quite interesting because if you keep scrolling through it, it will bring eventually up information about the last glacial maximum and the last glacial maximum on the British Isles. So these can be really useful to give an overview of the glacial landscape. But now we come to the interesting bit for me, which is what happens. We know basically. We have known for quite a few years that the ice sheet was actually flowing offshore, but we didn't know what was happening there. On the island of Ireland, we're quite lucky because we have access freely to lots of data sets offshore. They can be accessed from this website. So you can get digital elevation model of the seabed. You can get information about sediment distribution. You can download the data in different ways, so you can view them online in different ways. So 16, 17 years ago, myself and a colleague from the school here called Paul Dunlop, we actually started looking at all of this data and realized that a lot was happening offshore that we didn't know about. So really what we've shown is that the ice indeed extended offshore. The first year we went out with the ship was 2008, where we said, well, we have all of these landforms. We have moraines, we have drumlins up here, down here, so this is Donegal and Sligo. We have moraines of different orientations coming out of Killala Bay. We have ice scours all the way here. We have other things here that might be mega-scale glacial lineations or might not. But really, we can say this based on their shape, but really we don't have any proof. So we went out in 2008 for the first time, and we got some samples there, and I've got something to show you. And that was followed up by a larger project called Brit Ice Chrono that ran between 2012 and 2018, and we're just getting the last papers out, that really looked at doing a full reconstruction of the British Irish ice sheet, both onshore and offshore. So basically what we've seen, for example, Donegal Bay was the first area we looked at. We saw that at the shelf edge, so in around 200 meters water depth here, there's a really, really large moraine. It's about 125 kilometers long, 11 kilometers wide, and 40 meters high. So it's much larger than the moraines on land, but it's also because it was formed by a much larger ice sheet. Then we have a series of nested moraines here that suggest that the ice was retreating, the ice sheet was retreating in steps. So it stopped here for a while, formed an ice ridge, stopped there for a while, and retreated from the ice ridge. So we have these recessional moraines, and then we have a large kind of asymmetric morainic ridge over Donegal Bay, at the mouth of Donegal Bay, that possibly represented time when the ice was there for a bit longer. So by looking at the shape and looking at the dimensions, we can start thinking about where the ice was, how quickly it was retreating, in which way it was retreating, and all of this information is relevant for modeling the future. We also put together the data in Donegal with the data farther to the north, the Malin Sea, and we saw different orientations in these landforms that suggested there were two ice flows. There was ice flowing from Donegal here, but there was also ice flowing across the Malin Sea from Scotland. So as I said, in 2008, we actually went out and took quite a lot of samples across this area with a corer called the vibrocorer, which has basically a 6-meter metal barrel with the vibrating unit at the top. We lower this corer to the seafloor, so any water depth between 10 and 200 meters, or 250, the unit vibrates, it goes into the seafloor, and it took back, actually, diamecton till. So that was the first hard evidence of ice extending offshore onto the continental shelf. We damaged quite a lot of equipment in the process because this thing is very stiff, and we find some really large pebbles and cobbles that could only be brought there by a glacier. We actually have videos of this vibrocorer landing on an erratic on the seafloor that I don't have time to show you today, but I'm happy to share. So Brit Ice Chrono followed those kind of first evidence of glacial sediments offshore, but included lots of work done on land to date these landforms with these new techniques that we have, cosmogenic dating, luminescence, and so on, and also date more what is happening offshore, so dating more the sediments offshore. There were two key transits. I was involved in all of the work here around Ireland, but I mainly worked in the Malin Sea and Donegal Bay. And just to show you briefly what we did, as I said, we took samples offshore. Geologists, geographers, and so on, we always have good time when we are out onto the field. That's Paul Dudlow, a previous member of staff, Peter Wilson, who's just retired. There's a colleague there from Liverpool looking at sands, at proglacial sands over Donegal. So in this area, these are all the samples that we took. And what we can do now with this kind of data, we also took the samples offshore. So we sample similar sediments, similar glacial and glacial marine sediments on land and at sea. And we put everything together in this way. So not only we have all the mapped features, we have all the samples there, and all the results from the dating were treated statistically, doing something called Bayesian modeling that tries to match the dates. And from that, you can get isochrones. So you know more or less when the ice was at the shelf edge, when it was retreating, and you can start working out rates of retreat and hypotheses. So what we're interested in are what are the drivers of ice sheet changes. So interestingly, we found out that the ice sheet here was at its maximum extent before the last glacial maximum, which if you think about the last glacial maximum as the coldest period during the last glacial period, it's surprising. But interestingly, we also know that it started retreating before the last glacial maximum. So that will tell you that that retreat is not driven by climate. It's actually driven by other things, by other processes. And in this specific case, both across Donegal Bay and the Malian Sea, we think that the ice had grown so much that it was actually making the continental crust sink and therefore increase relative sea level. So that ice margin here was here around 26, 27,000 years ago, was grounded into 200 meters water depth. But it pushed that crust down, sea level increased, and destabilized the ice margin. By having more specific time intervals, we also know that the ice was standing at certain locations for longer periods of time, and those were probably driven by colder periods within the last glaciation. But we also know that actually it stood still around the mouth of Donegal Bay for quite a long time. So what was happening here is that we had headlands here and there that helped stabilizing the ice margin. So even if climate conditions were changing, the landscape, the topographic landscape, was driving the ice margin there. And then finally, as well, we can say by the different fossils that we find in the sediment that the final stage of marine deglaciation, again, were driven by local sea level changes. There's nothing in the sediments, nothing in the fossil that makes us think that climate was changing. So we know that, again, it was other drivers. And then finally, we know that the retreat on land was driven by climate, because by then conditions were warming up, and therefore there was that last push. So what? Why are we interested in all of these things? By putting together all of those data all around the UK and Ireland, we can come up with maps like this that represent the changes in the ice sheet over time and where it was melting faster and where it was melting slower, what was driving this change. And all of this data can then are actually being fed into ice sheet modelers that are looking at West Antarctic ice sheet, Greenland, and so on, which is way beyond what I do, so I'm not showing you any of that, but that's the process where we're taking the data. And I'll be very quick, because I know Paul is keeping an eye on me. I just wanted to show you one thing that I do with the students is to show them that they can look at any landscape outside of their window and know there are things there. One thing we do when we have lectures, we go out that way where you can see the river and you can see some of the glacial landscape. So we go for a tour from Coleraine around to Ballymoney, down up to Armoy, and then for Ballintrae and so on. And by doing this over the course of an afternoon, we really focus on visualizing the landscape around them and identifying landforms, correlating those landforms that they see with the satellite imagery that we have for the locations, and then learning to identify and describe glacial and proglacial sediments, and then start thinking about how can those sediments be linked to what processes. And then as well, consider the implications of what they're seeing for the sustainable management of resources. So lots of the proglacial sediments that we have around here are the gravel and sands that are used for constructions, both onshore and offshore. So they're there because the glaciers push them forward. So then that links back more to sustainable management, and there's also geoheritage that's linked to that. So which landscapes do we want to preserve? Why should we preserve them? So there's a lot that can be done at any location. So you see the example here, but that can apply everywhere. So this is a satellite imagery that we have of the north coast. Can you see a moraine there? Maybe you know where a moraine is there, but maybe you don't. Moraine is it's more of a morainic belt, so it's a series of different ridges that come together. That's called the moraine. So the students go around by bus and try to identify all these different ridges. So the moraine is the one marked in orange there. As I said, we go to Armoy and actually looked at some of the well-studied glacial sediments that we have there. We have a nice overview of the lands. We also can see from the satellite imagery actually that we have different landforms. So here we had an older ice flow from ice that was flowing from Ireland towards the coast, and that's given by the drumlins. And then we talk about how the shape of the moraine suggests that was made by ice that was coming across from Scotland. So we have an interplay here of different parts of the ice sheet. So we look at the landscape and we start seeing ridges and bumps and humps, and we talk about the shape and the size and so on. And then we go over to Port Ballintrae, where you have some nice outcrops of glacial and proglacial sediments. And I get them to do descriptions and try to put those descriptions together and try to see what they mean for glacial processes. So that's what we do. I have a series of other resources here that you might find useful. You might have some of those, you might not. The Antarctic Glaciers website is really good. It also has other stories about UK climate change and ArcGIS stories. And you can also take virtual glaciers, virtual glacial field trips. I find that it's really hard sometimes to visualize, for students to visualize these things without an ice there. So maybe going to locations like Iceland, even virtually, might help them to see that connection between the landscape that they see here and what's happening where you have a glacier. There's also a tool to create your own virtual field trip. If anyone is interested, give me a shout. It was basically put together by the University of Exeter during lockdown, and that could be helpful if you have students that don't want to go in the field, or you can't take them out to the field, but you still want to do a local field trip, virtual. That might be something for you to consider. It can be done with a phone or with a GoPro and so on. So that's me.